Learning the fundamentals of an operating system for IoT will help you prepare for today and tomorrow's IoT challenges. We'll begin by exploring the basics of an operating system for IoT, including the general characteristics, architectures, types, and some typical operating systems on the market. We'll look into the key topics with examples using a popular open-source operating system, FreeRTOS. These key topics include task management, inter-task communication and synchronization, memory allocation, timers, interrupts, and some debugging tools. I'm so excited to share that with you now. It is the most important computer software that manages hardware and software resources. IoT systems are essentially computer systems containing the key components such as processors, memories, and I/O devices, including storage devices, radio interfaces, sensors, actuators, etc. Many IoT and smart devices are using an OS for multiple applications across industry verticals. With an OS, these devices today tend to do more complex jobs than before. These jobs need to be efficiently handled. An operating system takes the role of reducing the barrier of managing tasks and resources, providing the interfaces for various hardware and software components. Let's see the scenario when no OS is used. Programmatically, it's possible to develop a program up and running without an OS, but we need to handle everything, including different tasks ourselves. We basically need to take care of a program from its start to its end before it's power cycled. If you view such program in a flowchart, we need to put all task logics into one infinite loop in order to keep it running. This approach is called super loop. In this way, if you want to do two tasks, such as reading the ambient temperature values from the sensors as task A, and processing and displaying the temperature histogram over time as task B, we need to put them two tasks into one loop. Of course, if we have more things to be done, we need to put them in the loop as well. In this approach, if we want to respond to real-time events, which is usually the case, we can still do so through, for example, an interrupt, which is an event triggered by the software or hardware component requiring immediate responses by the program. If we use another task C, like a service routine, to handle such interrupt, this can be illustrated in this flowchart, where the loop will be suspended in order to execute task C and then resume to run. All seems fine unless things get more complex. For example, we may have to deal with multiple interrupts and multiple tasks where they often need to share data between them. All these need to be carefully scheduled, but with the super loop approach, things are getting out of control easily, and codes get difficult to extend. Any changes made may cause your program unstable or erroneous. That complex scenario we've mentioned is exactly what today's IoT systems are facing. Today's software on IoT systems required to run on a single device is sophisticated. For IoT applications, we need some network connectivity options, such as Wi-Fi, Bluetooth, cellular, 6LoWPAN, CAN bus, etc., as well as the device management capabilities. We may also need to store data into our memory and a permanent storage device with a file system. We may need to have a graphic user interface on the display, and some mass processing capabilities, etc. At the same time, we also want the program to run smoothly and efficiently on the processor. At a high level, using an OS will benefit our IoT solutions in terms of the OS-centered technology ecosystems. An OS-centered technology ecosystem can enable us to use an application development framework and how they are linked to the OS characteristics. First, we require efficient management of multiple tasks and resources. It also relates to the system performance requirements. For safety-critical applications such as industrial control systems, the task execution needs to meet some strict timing requirements. Second, we may need to support various platforms in terms of software or hardware components. This is important in terms of the capabilities of an IoT device and its system design out of a broad range of hardware and software components on the market. For example, you may need to use a custom components or to upgrade your hardware components later on. An OS for IoT should make this happen with good extensibility. Third, support for various network connectivity options is a standard requirement of many IoT devices. An IoT device may work in one or more network environments, such as personal area, local area, and wide area networks. Then, we may also need a device to consume low power and to have a small footprint of an OS. This needs to support right from the IoT device level with an OS. Most IoT devices are small in size and memory, which therefore needs an OS to take small space without sacrificing the performance. Security is a standard requirement of IoT devices as well, which is supported by software together with hardware. Stability is also important for IoT devices, which may run for months or years. And last, we need to make the product development easily to conduct. All these user requirements can be mapped into the general OS characteristics. If we put characteristics in a more concise way, they are resource and power management, footprint, modularity and extensibility, portability, toolchain, and support, as well as licensing. Every OS may have a different weight on each characteristic in the radar chart, but let's look at them one by one first. Resource and power management. For IoT systems, the efficient management of computing resources and tasks is important for achieving a desirable system performance. This also relates to the power-efficient operations on some kernel tasks and support for power management capabilities working with the hardware. For example, an OS may provide an interface to invoke the sleep mode on the processor. Footprint means how much memory or storage space an OS will take. For small devices with limited memory and storage, an OS needs to be small enough. However, the OS should be configurable for adding more features. Extensibility and modularity. Extensibility means an OS is extensible for adding features and using some third-party software frameworks or libraries. Modularity means an OS supports a modular architecture to ease the extensibility and software customization. Portability. An OS should be portable for us to use a range of processors, hardware platforms, and I/O devices. Toolchain and support. The toolchain and support include the support for compiler and debugger tools, which are very important for software development. These may also include the out-of-the-box support from vendors. Support from the vendor and the user community is also important to OS users and developers. Usually, the good support for the US from the vendors and open source community indicates its healthy technology ecosystem. Licensing is another characteristic if you consider cost for your IoT product development and commercialization. There are quite a few open source embedded operating systems with permissive licenses, such as MIT license, Apache license 2.0, BSD-like licenses. Advanced, where many devices can run the general-purpose, full-fledged operating systems, such as Windows or Linux OS. A large portion of IoT devices belongs to embedded systems, which have specific tasks to run with limited hardware capabilities. A common question is which one should we choose? To answer this question, let's see the basic features of a general-purpose OS and an embedded OS. The general-purpose OS for IoT is an option for many applications, which, for example, require rich functionalities, run complex software, and use powerful processors and high-capacity memories. An embedded OS can be used for IoT devices requiring efficient resource management, high reliability with the support for low to high-end processors running simple or more complex software. Let's look at IoT elements to see the use scenarios of a general-purpose OS first. An IoT gateway is some device that is able to process large streams of data from various field devices. These requires a fair amount of computing power and energy. Therefore, powerful processors and memories are preferred. That often suffices the requirements of the general-purpose operating systems, where a Linux OS and other full-fledged operating systems are used. For other IoT elements, such as cloud computing devices, a general-purpose OS can be used as well. In addition, users can also benefit from the technology ecosystems established by the existing general-purpose operating systems. An embedded OS can be suitable for the field devices, including small embedded systems and resource-constrained devices, using microcontrollers or low-end processors only doing specific tasks, where their compute embedded device which has a long history and represents a strong ecosystem. Basically, an OS based on the Linux kernel can be considered as a Linux OS. A Linux OS is commonly seen on IoT network devices and high-end servers. You may have known some Linux OS distributions, such as Debian or Raspbian, Ubuntu, and Red Hat, running on the generic or regular devices. They are considered as full Linux. The other class of Linux OSs is generally called embedded Linux. It is used in cases where the devices have low-cost hardware and require optimized performance. Embedded Linux is used for the embedded systems with custom features less than those of full Linux, or with those using processors without memory management unit called MMU, while the full Linux is used for the processors having the MMU. MMU is a unit sitting between the processor and the memory, intercepting all memory references and performing translation between the virtual addresses and the physical addresses. Another thing that an embedded Linux is different from a full Linux is the support for minimal file systems and other features. Let's look at some typical embedded Linux operating systems. UC Linux now generally refers to systems using a Linux kernel and UC libc, where UC libc is a C library for embedded Linux. In comparison, full Linux kernel uses glibc, a set of core C libraries for the GNU system and GNU Linux system. Full Linux kernel requires the MMU and glibc, while UC libc is used when no MMU is used. Yocto project. Yocto is an open source project for creating custom embedded Linux distributions. There is embedded Linux development environment provided. It currently supports processors with the instruction set architectures such as ARM, PowerPC, MIPS, x86, and the 64-bit version of x86. OpenWRT is the Linux distribution meaning for wireless routers, which was initially released in 2004. It currently supports Wi-Fi and Ethernet network connectivities, as well as crypto software or hardware usually required on routers. The processors supported are based on ARM, PowerPC, AVR32, x86, etc. Android Things is a successor to the Brillo operating system announced by Google in 2015, while the first developer preview release was made in December 2016. Android things target at being part of the successful Android ecosystem. For example, the Android development environment can be used for developing Android Things apps, and the devices running Android and Android Things can talk to each other. Android Things is based on a Linux kernel with the hardware abstraction layer and additional Java API framework and the libraries sitting on top of them. It has out-of-the-box support for Bluetooth or IEEE 802.50.4, as well as Wi-Fi and Ethernet and transport communication protocols. Windows IoT Core was rooted from the embedded version of Windows, which can be dated back to 1998. As an optimized version of Windows 10 for embedded devices, Windows 10 IoT Core enables the IoT solutions in the Windows ecosystem. The current support of processors is based on ARM, x86, and x86-64. One of the important features of Windows 10 IoT Core is its support for Universal Windows Platform, which is basically an application architecture created by Microsoft for Windows 10. It means that you can use the Visual Studio to create one universal application that runs across various Windows 10 devices, such as smart sensors, gateways, mobile phones, and tablets. Windows 10 IoT Core also comes with some out-of-the-box support for security features, the cloud connectivity with the Microsoft Azure integration, and was created by Richard Barry in 2003. It's been broadly used in the microcontroller-based embedded devices. It had been released under a permissive license and now is released under the permissive MIT license, meaning that you are free to use it in commercial products without exposing your proprietary source code. The FreeRTOS kernel version 10 has become part of the Amazon FreeRTOS, meaning it's supported by the Amazon AWS ecosystem, which can be utilized for your connected solutions. Let's look at some feature highlights. First of all, it's a market-leading RTOS, which has been popularly used in many embedded projects. It has a small footprint, which takes a small portion of your memory on your board. The kernel only takes around 10 kilobytes of the read-only memory. It has efficient resource management mechanisms in terms of task and memory management, and it has an interface to use the low-power modes of processors. From the developer's point of view, its API functions are designed easy to use. It has a broad support for many processor platforms with a strong support from the industry and the user community. It is highly portable to a new processor platform because of its processor-agnostic architecture. It is flexible in choosing scheduling and memory management options that best fit your system requirements. It is highly configurable and extensible as well. For example, you can configure to only require the minimum functionalities, or you can configure to add more. It's extensible to use additional features. The FreeRTOS kernel does three major things: task management, communication, and hardware. Task management includes task creation, deletion, scheduling, and maintenance. Communication here means the internal communication between tasks, including the interrupt handling tasks and the interrupt service routines. We'll discuss such essential inter-task communication mechanisms later. The hardware part of the kernel are responsible for the interrupt management and generally hardware-independent and hardware-dependent functions. With this architecture, we can add the hardware-dependent codes and device drivers for various I/O devices and peripherals, such as radio interface modules, sensors, and actuators. We can also add additional software libraries on top of it, which are key to many today's IoT systems, such as communication stacks for networking, crypto libraries for security, such as data encryption algorithms and libraries for secure data transfer. We can also add additional libraries as needed. Based on the architecture, we can put an adaptation layer on top of the FreeRTOS kernel as well, in order to support some standardized programming interfaces. In that case, developers can write user applications running FreeRTOS, but using different functions from, for example, POSIX or SAMCs. In this example, we'll create two tasks named Task 1 and Task 2, and make them execute infinitely by repeatedly printing out some streams to the screen. Let's open the exercise file for this chapter. Then, open the win32.sln solution file with the Visual Studio. Now you'll see the project named Windows Example on the right side Solution Explorer pane in Visual Studio. Expand the example source node and open the file named main_app.c, which is the main program file we'll work on. Let's briefly look at the program, as we'll have the similar program for the later exercises. Although some codes have self-explanatory comments, to help you understand the code, I kept a few comments from the FreeRTOS source code. In the lines 2 to 3, we include the FreeRTOS kernel files, where FreeRTOS.h is the required include file, and the task.h is the header file for task management API functions we'll use in most FreeRTOS applications. Therefore, we'll basically need to include these two files most of the time. In line 6, we include the header file of supporting functions for the Windows port, which includes the printing functions for us to output some results to the console. In line 9, we define a large value used in the for loop to simply let a task delay for some time. From line 12 to 13, we declare two task functions were defined later in the file. Lines 18 and 19 define the streams to be printed out to the screen to indicate the running status of the tasks. Now, let's look at the main_app function from line 23 to line 31, where we created two tasks using the task creation API functions we'll discuss later, and start the task scheduler by calling the vTaskStartScheduler function. Normally, this function should never return until there is no memory space to create some kernel tasks. Then, from line 34 to line 55, we define the first task function, where it basically does nothing but it gets a string parameter we pass in and printed it out in an infinite loop. In line 47, the vPrintScreen function is the supporting function for us to display the string we pass in. The for loop from line 50 to line 50. Here I'm using have different meanings in different contexts. A task generally refers to a program, a unit of a program, a process, or a thread, which can be considered as a lightweight process. Some RTOS uses the term task or thread interchangeably. Programmatically, a task we referred to in this course is in the form of a sequential function with an infinite loop to do a specific job. But how to implement a task is application-specific, where it should be implemented to achieve the best system performance. For example, generally speaking, you may have multiple tasks in your program. One task collecting temperature data and storing it in the memory, and another task transferring the data to the cloud endpoint. The heavy duty of maintaining and controlling tasks is normally handled by an OS kernel. In this case, there are kernel tasks and the user tasks. Kernel tasks are the routine tasks required by the kernel, and the user tasks are defined by the users, such as the example data collection and transfer tasks we've just mentioned. Every task consumes the hardware processing resource in terms of CPU or processor time and memory. Let's see a simple example of multitask execution where 4 tasks numbered 1 to 4 execute sequentially without competing the CPU time. It's an ideal situation where, for any time unit, a CPU just needs to execute one task. It seems no issue on using the CPU resource in this example. Executing one task per time is simple, but in today's software, we usually need to let multiple tasks be executed concurrently. If we illustrate such task execution in an example, the 4 tasks may appear to have to be executed at the same time. How an OS deals with this concurrency scenario is the matter of task execution parallelism. Realistically, tasks don't take the same time. However, if we slice the CPU time into equal time slots, we can see that during some time period, 2 or more tasks still compete to use the CPU time. This can be considered as the extended case based on the last one. Let's look at how the task gets executed on CPUs. If we have only single-core CPU, the CPU cannot physically process multiple tasks at the same time. The way of doing this is to let the task take a share of the CPU time, so they can virtually execute concurrently. If we have a multi-core CPU, say a dual-core CPU, 2 tasks can be concurrently executed by the 2 cores at any time. But if we have more tasks for concurrent execution, for each CPU core, we still need to have a way of sharing the CPU time between tasks in order to let the tasks such as task 1 and task 3 or task 2 and task 4 appear to be executed concurrently. That comes to the multitasking concept, which is the concept of allowing multiple programs or processes to execute simultaneously based on the CPU time sharing. However, we didn't talk about how the tasks are running at each time slot. This is the responsibility of a task scheduler, which is part of an OS kernel. How the next tasks can run and how much time they can take are determined by a task scheduler. Every task scheduler is based on a task scheduling algorithm, also known as process scheduling algorithm. A task scheduler can be based on the 2 kinds of task scheduling algorithms, preemptive and non-preemptive. Preemptive task scheduling can preempt the current running task to allow another task to run. Conversely, non-preemptive task scheduling does not preempt the current running tasks, as it allows a task to complete before the other tasks get a CPU timeshare to run. A real-time OS usually uses the preemptive task scheduling algorithms for its task scheduler. Let's look at the typical preemptive scheduling algorithm called the round-robin. The round-robin algorithm allocates all ready-to-run tasks with equal time slots. It will preempt the task which takes more time than allocated time slots in order to let other tasks get a chance to run. The task that was interrupted will resume to run until it finishes. In an actual embedded IoT system, there are some tasks that always have higher priority to execute over others. For example, we may want to pre-assign the priority of the task taking the remote device management commands to have the highest priority in the user application. In order to put such priority into consideration, tasks can be modified in the data structure to take the priority numbers so that such highest priority tasks can always preempt the lower priority tasks, while the tasks with the same priority can still be scheduled based on the traditional round-robin algorithm. In fact, task priority assignment is a standard way of task creation API functions in many RTOSes, as you may have noticed in our first FreeRTOS example running on Windows. Let's see an example illustration of how multiple tasks get scheduled to execute on a single core CPU. by the priority-based round-robin task scheduler. The flow of the CPU handles multiple tasks is shown task is in the form of a sequential function or piece of program which is scheduled to run based on the task scheduling algorithm. The algorithm itself can be based on the priority-based round-robin algorithm or other ones. However, to actually manage a task by the OS kernel, more things need to be done. Let's talk about two important things here. First, the states of a task, and second, the context switching of the tasks when, for example, one task gets preempted by another task and then resumes to run later. A typical application may consist of multiple tasks, so we need to define the states of a task. In order to allow the kernel to basically differentiate the states that tasks are in and take some actions on managing them. Basically, every task has two states, running or not running. An OS schedules the tasks to transition between the states. In a multitask environment, a task scheduler in the OS kernel can schedule a task to run out of many tasks in the running states. If a task in the not running state wants to run, it needs to become into the running state to do so. However, if a task is in not running state, we don't know if it finishes actually, or it is preempted by another task. So, two states are not quite useful, and we need more states to be defined. In fact, the not running state can be further split into substates such as ready, suspended, and blocked. The ready state means a task is ready to run, but not running for now. A task with a ready state happens when a task is preempted. When a task is blocked, it is not running and waiting for an event to trigger it back to unblocked. The event can be sent through an inter-task communication mechanism or can be a timeout event. When a task is in the suspended state, the task scheduler will not consider it to run. A task may in the suspended state forever until it's resumed. These states can be transitioned from one to another through the task-related API functions. Note that we use the FreeRTOS terminology here for describing task states. A different operating system may use a different terminology, but the idea is the same as we introduced here. Let's talk about the concept of context switching. Basically, the kernel needs to make sure that the tasks which are suspended can be executed later. So there's some task-related context information needs to be stored somewhere and retrieved for such task switching. Let's further look at an example of what it means. We know that a running task can be preempted to switch into another task. If we have two tasks, task 1 and task 2, running as shown in this diagram, plus the kernel idle task running in the real-world scenario, the task 1 started to run first, then the first task switching happens when it's preempted by the requesting high-priority task 2. When such task switching happens, the OS kernel needs to do an important job in terms of the context switching to make sure each running task can be suspended and resumed to run successfully. More specifically, what an OS kernel would do is storing the context information of task 1 using the available computing and hardware resources such as registers in the CPU and memory and switch to the context of the task 2. After task 2 is done, it retrieves the context information for task 1 and switch it back to task 1. When there are no user tasks running, the kernel will schedule the idle task to run, which is basically doing nothing. Let's see an example of how to make two tasks having different priorities up and running. We'll use the exercise file for this chapter. Let's open the solution file of this chapter with Visual Studio. And then open the main_app.c file. This example is very similar to the first example we did before. Let's just focus on task-related stuff this time. In this example project, using the FreeRTOS task creation API function, we created two tasks here named task 1 and task 2, and pre-assigned them with different priorities 1 and 2 respectively, where in FreeRTOS, the greater the priority number, the higher the priority of the task. After we create the two tasks, they're ready but won't run until the vTaskStartScheduler function is called. Then, we can check the task functions for these two tasks. In line 30, we define the task 1 function, and from line 47, we define the second task 2 function. They're simply defined to take the parameters and run the infinite loop by just printing out the streams to the console. Let's just hit the run button and see what happens. Using the task state terminology we introduced, task 2 now is always in running state, and task 1 is always in ready state. Well, this is the way we program it, and what happens here is that task 2 is hijacking the CPU time because it has higher priority. A task scheduler, in this case, is doing what we program it to do. In order to make both tasks run, race condition. An OS usually provides interfaces in order to provide thread safety guarantees. The race condition happens when multiple tasks or threads trying to access or change the shared data. Here we show an example scenario of two tasks attempting to access the shared data globally defined as an integer with initial value of 1. Basically, task 1 and task 2 can change A at any time. If task 1 changes and uses the value in its task function, it will not get value it expected, because at any time, task 2 may change the value. This race condition is harmful to the program, which will introduce unexpected, erroneous issues and bugs. To avoid this to happen, we need to make sure when accessing the shared data, it is thread safe. Almost any operating system kernel includes the primitives for thread safe operations on shared data. Let's look at a couple of common options here. First, we can protect the data access by locking the data operations from other tasks. Second, we can use an inter-task communication mechanism to coordinate tasks to access the shared data. For example, if task 1 wants to access the variable A, it will find a way to inform the task 2 and so forth. The first option is straightforward. The idea is like this. When task 1 wants to access the shared data, it locks it from other tasks to access it. When it's done, it will release the lock. In this sense, we can create a section that prevents it from being changed by other tasks. The section is called critical section. An operating system usually provides primitives to create a critical section in order to lock the shared resources. As example, we can use the FreeRTOS primitives task enter critical and the task exit critical to do that, as we see here. Let's look at the second option in an example. Here, task 1 attempts to access the shared data, but it checks the event flag first to see if it's available. The flag, for example, can be a Boolean value of 1 to indicate the shared data is not taken by other tasks. Now, the event flag is set to 0, indicating it is being used by another task and not available for access by task 2. And this time, task 2 knows it cannot access the shared data by checking the event flag. When task 1 is finished accessing the shared data, it will signal to reset the event flag back to 1. At this point, task 2 can access the data. In this way, the access to the shared data can be coordinated between task 1 and task 2, and the race condition can be avoided. It is also possible to coordinate multiple tasks to access the shared data through various inter-task communication and synchronization mechanisms. Let's look at an exercise. In the exercise, we'll see an example of how to use the first option to protect our data access from other tasks. So let's open the exercise file for this chapter. In this example, we still use two tasks, task 1 and task 2, but we define a string called shared data as a sample shared data accessed by both tasks. Let's briefly look at the task functions. In line 36, task 1 is simply changing the value of the shared data to indicate it's changed by task 1 and printed out value to the console. So the shared data at this point gets changed in the code at line 58. In line 69, we make the task delay for 300 milliseconds. After that, in line 71, we compare to see if the shared data we just changed is changed or not. The expected result is that when the shared data gets changed by task 1, it should remain the same in task 1's function. We use the config assert macro to indicate the undesirable case when the shared data is not the same as we expected. And the assert macro helps us to better debug the program, as sometimes it's not easy to spot that on the console outputs. From line 82, the task2 function is defined to do nothing but repeatedly change the value of shared data to simulate the race condition scenario. Right now, it's not easy to say whether we'll exactly experience the error message thrown by the assert macro in the task1 function or not. So let's go ahead to build and run the example. Deadlock. It is a state that usually results from multiple tasks waiting for another task to make a move. It can happen when we mistakenly use an inter-task communication mechanism to access resources shared between tasks, or it can happen on a single task. Let's see a typical example when a deadlock happens. Suppose we have signals S1 and S2, and the resources R1 and R2, being held by task 1 and task 2 respectively. Now, task 2 attempts to access the resource R1 taken by task 1, but it needs the signal S1 from task 1 to do so. And task 1 attempts to access the resource R2 held by task 2, but still it needs the signal S2 from task 2. However, task 2 didn't get signal S1 and now is in the blocked state. So did task 1. In this situation, both tasks will be blocked and not get executed as we expected. A deadlock can be avoided if the tasks and the resources to be used are carefully checked. Any resource being held by a task needs to be freed with the correct procedure. For example, in FreeRTOS, if we take the semaphore to lock the resource, we need to give it back. Let's see an example of a deadlock. Let's open the exercise file and look at the main app.c file. We use a task notification API to synchronize tasks this time. The use of task notification in our case is very easy. Task 1 and task 2 functions look very similar, but they have a little bit difference. Task 1 will give a notification to task 2 at line 44. And then, in line 47, it blocks itself until it receives the notification from task 2. While task 2 does the opposite stuff. It blocks itself first until it receives a notification from task 1, and then send a notification to task 1 to unblock the task 1. Now let's run the program. The program works well, and task 1 and task 2 will synchronize themselves in the execution perfectly. We can see the pattern from the console results. Let's try to make a deadlock situation here. For example, let's not let task 2 inter-process communication mechanism, which allows multiple tasks or processes to communicate with each other. It can be used to send messages between tasks and interrupt service routines. In an example scenario, we have two tasks, task 1 and task 2. Task 1 can send a message to task 2 through the use of a message queue and vice versa. The message queue can have a size of 1 or more, depending on how you want to share messages between the tasks. If a queue has a size of 1, we may use a queue to implement the mailbox. Now, let's look at an example of how to use a queue to pass a message between two tasks. In particular, how to send a message from task 1 to task 2 using a message queue. Let's open the exercise file for this chapter. Open the solution file with your Visual Studio, and let's look at main_app.c. In order to use a queue in FreeRTOS, we need to include the file queue.h as we see in line 4. Then, we define a message struct to be put to the queue later, in line 21, as well as the queue length and item size of the queue in line 27 and line 28. We also need to define the queue handle named xq1 for the queue. Then, in line 37 and line 38, we still created two tasks, named task 1 and task 2. But what's different here is we have different priorities, and also we're using the task handles, because we will use the handle to differentiate different tasks we're going to send a message to. Next, in line 53 of the task 1 function, we'll create a queue using the xQCreate API function, where we pass queue length and message item size parameters. This function will return the queue handle and assign it to xq1. Then in the for loop, in line 61, we first delay the task 1 for a brief time period, such as 500 ticks, and print out the string to indicate the task 1 is running. In line 66, we'll create a message with the counter ID and the message string content, say hello IoT. In line 69, we use the API function called xQSendToBack to send a message we just created to the queue, where the first parameter is the queue handle. The second parameter is the pointer to the message item to be put to the queue. And the third parameter is the waiting time for the task to block itself if the queue is full. Here, we just send a message immediately without waiting to block the task 1. So we pass a 0 to the third parameter. Let's see how to retrieve the message in the queue from task 2 using the API function called xQReceive. In line 89, we use the API function and pass the queue handle to the first parameter, followed by the buffer defined in line 77, where the message item in the queue will be copied to. The third parameter is an intertask communication mechanism, which means the mutual exclusion among tasks when they access a shared resource. A mutext can be implemented as a token. When a task seeks to access a resource shared with another one, it has to obtain a token to do so. Let's look at an example to see what it means. Suppose we have task 1 and task 2. They attempt to access the shared data, but we know that they cannot do so simultaneously. Or in other words, there should be mutual exclusion to make sure the shared data can only be accessed or changed by one task at any time. In this case, using the token to allow only the task having the token to access the shared data can make things happen. Task 1 gets the token to access the data. The shared data is locked to task 1, so no other tasks can access it. When task 1 is done accessing it, it passes the token to task 2. Now only task 2 can access the data. Semaphore is an inter-task communication mechanism that can be considered as a generic mutex. It can be used for mutual exclusion and more, such as counting events and managing resources. For example, we can use it to count how many data packets we received from the network, which are ready for processing by our task in the network application. Semaphores are usually classified into binary semaphores and counting semaphores. A binary semaphore is the semaphore with count value up to 1, while a counting semaphore can have a count value greater than 1. They are used in different scenarios. Let's see how to use semaphores in FreeRTOS. First, we need to create a semaphore, either binary semaphore, a counting semaphore, or mutex, using the corresponding FreeRTOS API functions listed on the right. After the semaphore is created, we can use it in task by taking the semaphore. Then, we can do something, for example, manipulating the shared resources. After the task is done using the shared resource, you can simply give the semaphore for another task to use. Note that you don't need to give a binary semaphore back. To give a semaphore, we call the API function simply xSemaphore_give. Let's see an example of how to use the semaphore for mutual exclusion on the shared resource. We'll use the XSS file for this chapter. So let's open the solution file in the folder with the Visual Studio. The main file is similar to what we did in the previous chapter, but we're replacing the critical section primitives with the FreeRTOS semaphore mutex API functions. First, in order to use the semaphore-related API functions, we need to have the include file for that. We include this file at line 4. Then in line 25, we create a semaphore handle for it to be created later. In line 29, in the main add function, we simply create 2 texts with equal priorities. In line 54, we actually create a semaphore for mutex using the API function we saw before. In line 72, we must first take the semaphore before giving that. In line 75, let's do something on the shared data. So here we just change the shared data to some other stream, indicating it's changed by task 1. In line 91, we finished modifying the shared data and now release the semaphore by calling the API function xSemaphore_give. The only parameter we pass in is the semaphore's handle. Key computing resource for keeping the kernel and the user applications up and running. Therefore, it's important to know how the memory is managed by an OS. In a computer, the memory is basically the hardware for information storage and retrieval. We have 2 kinds of memories. The first is volatile memory, used as the main memory of the computer for temporarily storing information at a high speed. And we also have non-volatile memory, which is the memory storage that can hold the data permanently. The typical example is flash memory. In order to save the information, memory storage device is split into sectors and blocks, usually in data units of bytes. Managing these memory blocks is not a trivial job, and is often handled by a memory allocation algorithm supported by an OS. The OS kernel will manage the memory usually in order to save and retrieve data efficiently. A fundamental job is efficient allocation of the memory. Memory allocation is responsible for determining the useful memory, allocating and managing the memory space. The goal is to make an efficient use of the available memory space. Without doing it carefully, it may cause the memory fragmentation problem, making the available memory fragmented into small blocks, which may not be useful. To understand all this, let's look at how the memory is organized from an operating system's perspective. First of all, in addition to the memory block concept, which is related to the physical organization of the memory can be considered as a static and a dynamic memory space. Static memory is a piece of static memory pre-allocated at the compile time, and heap memory is a piece of memory for dynamic allocation, while stack and heap memory space can both be available in the memory, such as random access memory, of your computer. At runtime, some operating systems may manage a pool of memories to be allocated dynamically in heap, or it can use a different way to manage that. When allocating memory in heap, memory fragmentation is a common issue that needs to be addressed by the memory allocation algorithms. In FreeRTOS, you can configure to use a static or dynamic allocation depending on your application requirements. In some small embedded systems, because we don't dynamically create and delete many tasks, static memory allocation may be efficient enough. Let's look at API functions for us to dynamically allocate memory space. This API function is called pvport.malloc. In FreeRTOS, in order to provide flexibility, from version 9, the dynamic memory allocation is put in the portable layer, allowing users to implement their own algorithms. Let's look at an example in the exercise file. We'll see how to dynamically allocate memory using pvport.malloc function to create a buffer to hold the received data sent by a task. The task can be any task in your IoT application in reality, such as a task giving time series temperature data or Bluetooth or Wi-Fi data you received. In the example, we actually do something useful by passing data from one task to another using the stream buffer, which can be created in a heap memory space. Well, stream buffer is the FreeRTOS feature that allows data to be passed between tasks and interrupt service routines. Now let's look at the source code. To use a stream buffer API, we need to include the streambuffer.h file at line 4. Then, we define the size and handle of the stream buffer in lines 18 and 19. Then we create the two tasks. In the task 1 function, we create a stream buffer in a heap memory in line 44. And then, we create some message to be sent to the stream buffer in lines 58 and 59. So the messages will look like hello IoT 1, hello IoT 2, and so on. In line 63, the message gets sent by the stream buffer. Now let's see how the messages are received in task 2. But we didn't talk about how the OS manages dynamically the heap using the memory allocation algorithm. There are classical algorithms for memory allocations. Every algorithm has its pros and cons. I'd like to introduce the typical first-fit algorithm, which is used in FreeRTOS. Let's see how the first-fit algorithm works. Suppose we have a heap memory space. The OS will maintain a heap memory and allocate and free them dynamically. The memory space has 5 memory blocks with different sizes. First-fit algorithm allocates memory like this. If we want to request 50 kilobytes of memory, it finds the first available memory block that can be a fit. So in the current heap memory space, the first memory block doesn't fit, but the second one does. Then, the memory is allocated. After the user finishes using it and frees it, it becomes available again. In another example, if we have a memory space like this, to allocate the 50 kilobytes of memory space, the first fit algorithm will still find the second block as a fit. But this time, the remaining 50 kilobytes of this memory block can be available for other users. In FreeRTOS, the memory allocation algorithm is portable with predefined schemes. And often needs to connect many different kinds of external devices and peripherals All these devices are viewed as input and output, or I/O devices. Let's look at the possible I/O devices for IoT. We may need a storage device to permanently store some data as well as the programs, using such as SD card, flash memory, or solid-state drives. It is also common to see some radio modules on IoT devices as well, which can be radio transceivers, such as Bluetooth transceivers or other ones, LTE modems for a cellular IoT communication, etc. These modules may be included in one chip with your CPU and memory in a system-on-chip solution. Then we have some typical input devices such as sensors, including temperature sensors and GPS and cameras in general. We also have actuators, sometimes considered as output devices. For example, we can have motors and water valves for IoT-based robots and industrial control applications. In addition, we may have some other I/O devices, such as display or touchscreen. Now, let's look at how physically the I/O devices are connected to the CPU of the board. Simply put, they connected to the CPU as peripherals through the analog or digital interfaces, although there are some extra electronic circuits required. Different devices provide different interfaces. Some are analog while some are digital. For the devices providing analog interfaces, we need to interact with them in analog signals. For example, the analog signals called PWM stands for pulse width modulated signals are commonly used to control the motors. For the devices providing digital interfaces, which are commonly seen on most sensors nowadays, we communicate with them in digital signals. Let's look at how an OS deals with the input and output devices. Based on the OS system architecture, it can provide a programming interface in the hardware code of the kernel to operate a device using the device drivers. An OS also needs to have a mechanism to handle the real-time events in the form of interrupts. These events, for example, include the data reception events from the network, reading the sensing data, and reading the buffer from the serial communication port of digital sensors. When that event happens, the devices can generate interrupts to be taken care of by the interrupt service routines in the software. The way the OS handles the interrupts is providing some mechanisms to handle the interrupt service routines. An ISR can be considered as a special task, and it usually needs to share data with regular tasks, but they may use a different set of API functions to do that. Let's take a look at ISR further. An ISR is in the form of a function in your program, and it can interrupt the tasks in order to respond to real-time interrupt events. For example, if a cellular modem on your IoT device receives some commands from an unauthorized entity that is several kilometers away to control the streetlights, we need the OS program to respond to that quite quickly. Such timing requirement is more common for the safety-critical applications. In addition, the OS kernel has a mechanism of how to do the switching between an ISR and a task being interrupted by the ISR. An ISR and a regular task may share data which may require thread-safe operations. Note that in FreeRTOS, a different set of API functions is used for ISR functions. First, communication with the regular tasks. The best practice suggests keeping the ISR as short as possible in order to not interrupt the tasks for too long, and to give the chance to other interrupts. Now, let's look at how the ISR is done and how it interacts with tasks. Let's open the exercise file for this chapter. Open the main_app.c file and see an example interrupt handler function. In this program, we show that how an ISR works and how to let ISR communicate with a task. To do this, we created two tasks from lines 48 to 49. And we also create one ISR, which is simulated by the handler function defined at the line 25 and installed at the line 52. Since we're working on the Windows simulator of FreeRTOS, we use task 1 to simulate the periodic interrupts to be handled by the ASR, which is the handler function here. This is done at line 71. Task 2 does nothing but block itself until it's notified by the ASR, which can be seen in the code at line 86. After it prints out some streams to the console, it's blocked to wait for the notification again from the ISR. The communication between the task and process in the software and the embedded system development when we may deal with the hardware components. It is the process of identifying and removing errors from your software. It's very useful for RTOS applications. For example, for multitasking OS-based applications, some tasks may not be running as expected, and it's hard to spot something wrong without tracing the tasks to check the timing and context switching information of our task. Sometimes we can simply debug an application by printing out the variables to watch them through the terminal or serial ports. But that approach doesn't work well, especially in complex software. Thus, we need more functionalities when debugging a program, such as watching data in the registers and memories, setting breakpoints to the code, and stepping through the code. Now, let's see some debugging options. In general, we can use the software debugging tools, such as the GNU Project Debugger, GDB, which is powerful for us to examine and monitor the program execution. We can also use a tracer tool to show a history of instructions. There are many software debuggers and tracer tools available on the market. Tracing would be very useful for the RTOS-based applications, as we may need to check the timing of some events and the task scheduling, states, and context switching, as well as the usage of a memory and interrupts. The debugging process can be enhanced with the hardware-backed solutions. For example, with the JTAG or SWD hardware interfaces on the board, we're able to check the program execution at the CPU level and test the circuit board interconnections between the chips. There are many JTAG or SWD-based adapters using the JTAG or SWD interfaces on the board. These products include the J-Link debugger probes, which provide an interface to allow the program running on the target board using the JTAG interface with the compiler and debugger software on the host computer. The board NRF51DK we used in the course has a J-Link onboard debug probe. For the program based on an operating system, we may use debugging features or interfaces provided by the OS. FreeRTOS provides some API and utility functions for us to debug a program better. For example, as tasks are important to our FreeRTOS application execution, we can check the task execution with some API functions. And also, we can check the task information when switching between the tasks. We can also use the tracehook macros to monitor our embedded application, including the task execution. There are some tracehook macros a good foundation for IoT systems and solutions. For the next steps, you can explore more of the operating systems introduced. Learn more about FreeRTOS features and practice them on the Windows port we used in the course. There are manuals, support documents, and source code repositories available on the FreeRTOS website and on Amazon FreeRTOS GitHub page. You can work on an actual development board, as what I have used in the course, with a FreeRTOS port. If you have a new board without FreeRTOS port, you can check articles on how to port FreeRTOS with the board information from the vendor or manufacturer. Also, I encourage you to check out my other courses on IoT foundations, such as IoT Foundations Low Power Wireless Networking and IoT Foundations Device Management.